Dividing complex numbers is an odd process because there's simply one big rule that we have to make sure that we adhere to. That big rule is that we can have no imaginary numbers or no i's in the denominator. If we see an I in the denominator, we have to do all we can to get rid of it. And that is dividing and simplifying complex numbers. So what does this look like? Well, if I had an example like 6 divided by I. I noticed right away that I have this imaginary in my denominator. So I think, how do I get rid of an I? How would I make it into a real number? Well, I know that I times I is I squared, and I squared equals -1. So if I multiply the bottom by I, I'm going to get rid of the imaginary number. But in order to make sure that I don't change my fraction, I also have to multiply the top by I. Because we know that I over I is really just the number 1. A really complicated way of writing the number 1, but it's the number 1. So if I do the multiplication in numerator and denominator, I get a positive 6i in the numerator, and I get I squared in the denominator. And since we've been dealing with complex numbers for so long, we know for sure that I squared is really -1. So if I simplify this answer, I have 6 divided by -1, which is -6, and I. And I notice here that I have a denominator of +1, which does not have an imaginary number in it anymore. So that's a simplified dividing complex numbers problem. Something a little bit more complicated would look like 8 minus 6i, all divided by 14i. When I go about doing this problem, I look at the denominator and I see that I'm breaking the big rule. I have an I right here, but I also have a 14, and I'm fine with the 14. I can just leave that in my denominator. So I'm going to take the same process I just used and multiply top and bottom by I, because that's going to get rid of the imaginary number in the denominator. In the numerator, this process got a little bit more complicated because now I have to distribute that I to both of those pieces. That gives me 8i minus 6i squared. And I'm getting pretty good at this now, where I can stop and realize that -6i squared is really just +6, because I squared is -1, and then you would multiply. In the denominator, I now have 14i squared, or if I like to think of that quantity as one piece, it's going to be just -14. So we clean this up, and what this really looks like, if I write the numerator with the real part first, is going to be 6 plus 8i all over -14. And now at this point, I've adhered to the big rule. I've gotten rid of all the imaginaries in the denominator, but I need to go through and simplify this in terms of reducing my numbers and getting rid of this negative right here in the denominator. So the first thing I'm going to do in terms of reducing this example is I'm going to reduce from all 3 of these places right here at the same time. If all 3 of those numbers don't reduce by the same number, then I can't reduce my complex number fraction anymore. So when I go to reduce, I see that they each are divisible by 2, which leaves me with a 3 plus 4i all over -7, which is more simplified. But now I have to deal with this negative sign here. I can treat him like a -1, and mathematically we like to distribute that either to the numerator or just yank it out front. I'm going to distribute to the numerator, which changes the sign of the 3 and the 4i, and it makes the 7 a positive in my denominator. And this is a much more mathematical answer than what I had before. And it adheres to the big rule. There are no imaginary numbers left in my denominator. If I look at something a little bit more complicated, where I have a full complex number, 3 plus I in the numerator, and a full complex number, 4 minus I in the denominator, I run into a slight problem. If I try to use that same method I've been using with I on top and bottom, I'm going to run into a problem whenever I go to distribute him in the denominator. That I times that I will give me a real number, but when I distribute the I to the 4, it's going to put an imaginary number in my denominator. And remember, the big rule was no imaginaries in the denominator. So I'm going to have to go ahead and I'm going to have to find another process that's going to get rid of that imaginary number. And if I think back to multiplication, there is one thing I can multiply an imaginary number by in order to get rid of the imaginary part. In this case, it's the conjugate, 4 plus I. And remember, if I multiply by the bottom, I have to multiply by the top. so I do not change the fraction. So here, again, I'm going to be looking at the complex conjugate, where I change the middle sign. That's going to take my complex number and make it into a purely real number. So all I need to do now is I need to FOIL twice. 4 times 3 is 12. 4 times I is positive 4i. 3 times I is positive 3i. And I times I is I squared. And we know that I squared is negative 1. I'm just going to treat him as a negative 1. Look at the denominator. I FOIL that out. I have 4 times 4, which is 16. I'm going to put the middle terms in, though I might not always, because they're going to show me that they cancel out. 4 times negative I is minus 4i. I times 4 is plus 4i. And I times negative I is negative I squared, where I have to be a little bit careful because I squared is negative 1, but there's this negative sign. So this whole quantity is really positive 1. So there's one more step before I get my final answer. Combine like terms on top and bottom. I have a 12 and a negative 1 on the top, which gives me an 11, and plus 7i from the imaginary parts. On the bottom, I know that the imaginaries cancel out because I used the conjugate. So I have 16 plus 1, which is 17. And last but not least, I just have to check to see, do I have a reduced fraction? So I look at those 3 places, and they have no common factors. So I know that I have a reduced fraction for my answer, and it adheres to the big rule of no imaginary numbers in the denominator. So that's my final answer.